In this video, we're going to talk about parametric equations of lines. Now, a line can either be in 2 space, right, in the plane, or a line can go through 3 space. But in either case, we can determine a line uniquely by specifying a point on the line and a direction that the line is going in. Okay, so the direction is really indicated by a vector. Now, I've put the vector here, AB, along the line, but of course you could think of a vector as going out from the origin. And so what we'd say is that this line is parallel to this vector. What we mean when we say the line is parallel to the vector, we mean the line goes in the direction of the vector. So notice once we specified a point, okay, x naught, y naught, we're in 2 space here, and a direction of the line, that gives us the line completely. Okay, we know exactly what the line is. Okay, now it turns out that every point on this line, could be thought of as a vector, right, going from the origin to that point. And so every point can be thought of as this vector, okay, x naught, y naught, plus some multiple of this vector. So for example, this point right here could be thought of as this vector x naught, y naught, plus, looks like about 2 of these AB vectors. So in other words, x naught, y naught plus 2AB would get us to this point. Plus 3AB would get us to this point over here, or 1.5AB would get us here. Now, x naught, y naught plus 1AB, that would get us to right here. X naught, y naught plus 1/2 AB would get us to here. X naught, y naught plus 0AB would be here. And if you take negative values, okay, something like -1 times AB, it would give us points out here in the other direction. So notice every point in the line has this form, x naught, y naught, plus some constant times AB. Okay, some constant, I just called it t. Now t doesn't have to be a whole number like 0, 1, 2, 3. It could be a fraction or a decimal. It could be negative. But notice we could rewrite this x naught, y naught plus TAB as x naught, y naught plus AT/BT. Okay, and then we can add these 2 vectors and write it as x naught plus AT, comma, y naught plus BT. So notice this is the x coordinate and this is the y coordinate. And actually these are parametric equations for that line. X equals x naught plus AT, y equals y naught plus AT. Now remember, x naught, y naught was this original point that we had along the line. And the A and the B were the components of the direction vector. Okay, so here's a theorem. And by the way, this also works in 3 space. I'll draw a picture for that. So in 2 space, the line that passes through the point x naught, y naught in the direction of the vector AB, or AI plus BJ, has parametric equations x equals x naught plus AT, y equals y naught plus BT. And you can do a similar thing in 3 space. Okay, so notice what the picture looks like in 3 space. You have this point out here in 3-dimensional space, x naught, y naught, z naught, and you have a direction vector, and this line is passing through 3-dimensional space here. Okay, but once you specified that point and the direction that the vector that the line is facing in, you've determined what that line is completely. Okay, so the line that passes through the point x naught, y naught, z naught in the direction of the vector ABC, okay, has parametric equations this. Okay, x equals x naught plus AT, y equals y naught plus BT, z equals z naught plus CT. Okay, now by the way, you could come up with other parametric equations for this line. You could have picked a different point on the line. Your ABC could have been maybe longer or shorter. Okay, so these parametric equations are not unique. Okay, but once you have a point and a direction vector, you can come up with parametric equations for the line. Okay, so let's do a couple of quick examples. Find parametric equations for the line that passes through the point 4, 2, and is parallel to the vector -1, 5. Okay, so I'm not even drawing this here, but you can maybe draw this on a separate sheet of paper. Draw the point 4, 2, and then draw a vector where you go to the left 1 and up 5, and then draw in that line. Okay, what are parametric equations? Well, the x naught, y naught is 4, 2. Okay, and the AB is -1, 5. So our parametric equations are x equals 4 plus a -1t. Okay, and y equals 2 plus a 5t. Okay, and we can do the same thing in 3 space. The line that passes through this ordered triple here, 1, -6, 3, and is parallel to this vector. Now I've written in IJK notation, but it's really 4, 5, -7. Okay, that's what our ABC is. Okay, and our x naught, y naught, z naught is 1, -6, 3. So our parametric equations are x equals 1 plus 4t, y equals -6 plus 5t, and z equals 3 plus a -7t, or just 3 minus 7t. Okay, but now what about a question like this? Find parametric equations for the line that passes through 2 points. Okay, so just imagine 2 points lying out in three-dimensional space. And by the way, I have not carefully drawn where these points are. In fact, this point is clearly not right. So 2, 4, -1, it's down below, right? It's the z coordinate is negative, so it's you know, down here somewhere. But I'm not trying to draw where these points are perfectly. But suppose you have 2 points in three-dimensional space, and you want to find what are parametric equations for the line that goes through those 2 points. Well, remember, the 2 things that you need to know to find the parametric equations are 1 point on the line. In fact, we have 2 points, so all we really need is 1. But then a direction vector for the line. So the way that we can come up with a direction vector is to use just this vector P1 to P2 as our direction vector. And remember, the way that you find this direction vector is you subtract the coordinates. You do the coordinates of P2 minus the coordinates of P1. So P1, P2 is going to be 5 minus 2, which is 3, comma 0 minus 4, which is -4, comma 7 minus a -1, which is 8. Okay, that's our direction vector. That's what we'll call our ABC. It's 3, -4, 8. Now our x naught, y naught, z naught is we just pick one of these points. Actually, you could really pick either one. So whether the vector were emanating from this point or is going out from this point, it doesn't really matter. Okay, so let's just use the first one. So we have 2, 4, -1 as our x naught, y naught, z naught. So notice parametric equations are x equals 2 plus 3t, y equals 4 minus 4t, and z equals -1 plus 8t. Okay, now the other question was, where does this line intersect the the xy plane? So look at the xy plane down here. And again, my picture's off here, but where would this cut through the xy plane? Now notice a point is on the xy plane if and only if the z coordinate is 0. Okay, so what we need to do is set z equal to 0. Okay, if we set z equal to 0, what value of t makes z be 0? Well, we let 0 equal -1 plus 8t. We solve that for t, and we get 1/8. So it's when t is 1/8 that we're actually right on the xy plane. Okay, so let's plug in 1/8 for t in each of these cases here. So if we plug it in for t, the x ends up being 19/8. Okay, 2 plus 3 times 1/8 ends up being 16/8 plus 3/8 is 19/8. And if you plug in 1/8 here, you end up getting 4 minus 4/8, or 4 minus a half. That's 3.5, or 7/2. And then the z, of course, ends up being 0. You don't even have to plug in the 1/8. We already know the z is going to be 0. But if you did plug in the 1/8, you'd see you have -1 plus 8 times 1/8. That'd be -1 plus 1 is 0. So this point here is the point where our line crosses through the the xy plane. Okay, now let's consider these parametric equations. Okay, so I've drawn them here. We could rewrite this in a sort of vector form. So notice we could rewrite the equation x equals 3 plus 2t like this. We could write xyz equals something, comma, something, comma, something, and the x was 3 plus 2t. Okay, now the y was -5 plus 8t, and that's what we're putting in the y coordinate here. And then the z is 7 plus 9t. Okay, now we could write this another way. We could write this vector as the sum of 2 vectors. We could write it as 3, -5, 7, plus the vector 2t, comma 8t, comma 9t. And in that last vector, you could sort of factor out the t, right? Write it as a scalar multiplication of t times the vector 2, 8, 9. So notice we could rewrite this as a vector equation. Okay, so we went from these parametric equations to an equation that involves vectors. And notice this last equation has the form r equals r naught plus tv. Now the r and the r naught and the v, those are vectors. The r is really just x, y, z. The r naught is the 3 minus 5, 7. Okay, if you go back up here, it was these numbers right here, 3 minus 5, 7. That was our r naught. And the t is the 2, 8, 9. If you go up here, I'm sorry, not the t, the v is the 2, 8, 9. Those are the numbers right here. Okay, so this is called the vector equation of the line. So we can rewrite those parametric equations as a vector equation. And by the way, you can also go vice versa. You can start with a vector equation like this and rewrite it as parametric equations. Okay, so another way to think about this in terms of the vector equation is you have this r naught, which is 3, negative 5, 7. So this point right here would be the ordered pair, 3, negative 5, 7. And then this v is the direction vector that you're going. And the generic point on your line is the xyz. So this point here could be any point along this line. This point xyz has the form r naught plus some multiple of v. So it almost looks like we have maybe 1, 2.5 of these v's. So for this particular point, this r is equal to r naught plus 2.5 times v. Okay, but the point is any point along this line could be thought of as r naught plus some constant times v. Okay, in this case, right there, that point is 2.5. Okay, and again, we could rewrite this equation that I just mentioned, this vector equation, in the ijk notation. It's always good to be able to move back and forth between the brackets and the ijk. So we could write this as xi plus yj plus zk is equal to 3i minus 5j plus 7k plus t times 2i plus 8j plus 9k. Okay, so it's always good to be able to translate back and forth between those different notations. Okay, let's do an example. The equation xyz equals 8, negative 2, 5 plus t times 4, 0, 6 is of the form r naught, or r equals r naught plus tv. So this is the r, this is the r naught, this is the v. Okay, so the equation represents a line in 3 space that passes through the point 8, negative 2, 5. And by the way, notice that's what you get when t is 0. Okay, when t is 0, go back up here. Notice if t is 0, what do you get? Well, if you're doing 2.5 of these v's, you get here. If you're doing 1 of the v's, you get here. If you're doing 0 of the v's, you just get r naught plus 0v. You end up just getting r naught. Right? So notice if t is 0, you just get r naught. Okay, if t is 1, you would get this point. If t is 2, you get this. If t is 2.5, if t is negative 1, you get over here, negative 2, and so forth. All the points along this line, though, are of this form for different values of t. Okay, so let's do another example here. So express the parametric equations. Now these are parametric equations in 2 space here, in vector form using bracket notation, and also in vector form using the ijk notation. So x equals negative 3 plus t, y equals 4 plus 5t. We could write it in vector form using bracket notation as xy equals negative 3, 4, okay, negative 3, 4, plus t times 1, 5. Okay. Notice, by the way, if you combine this on the right-hand side, this would give you negative 3, 4 plus, it'd really be t comma 5t. Okay. And then if you add those vectors, you get negative 3 plus t, comma 4 plus 5t. And the x would be the negative 3 plus t, and the y would be the 4 plus 5t. Okay, now we could also rewrite this with the ijk. So instead of writing xy, we write xi plus yj. And instead of writing negative 3, 4, we put negative 3i plus 4j. And same thing over here. Instead of putting 1, 5, we just put I plus 5j. That's 1i plus 5j. Okay, now how can we kind of go in reverse? So suppose I give you the vector equation of a line, and I've written it in the ijk notation. Can we rewrite parametric equations for the line? Well, yeah, notice the left side is just xyz, and the right side is 0, 1, 4. Now, why is there a 0? Well, it's 0i plus 4j plus 1k, and then plus t times 3 minus 1, 2. Well, notice you can do this scalar multiplication, multiply by the t, and what you do is you multiply each component by t, so you get 3t minus t, 2t. And then when you add these two vectors, you add them component-wise, so you get 0 plus 3t in the first coordinate, 4 minus t in the second coordinate, and 1 plus 2t here. And notice what you end up with is that the x is 0 plus 3t. Okay, and by the way, you could just write it as x equals 3t, but it's 0 plus 3t. Y equals 4 minus t, and z equals 1 plus 2t. Okay, and our last problem here. Find where the line having parametric equations x equals -2, y equals 4 plus 2t, and z equals -3 plus t intersects the xy plane, the xz plane, and the yz plane. Okay, so first of all, to find where this line intersects the xy plane, we need to set z equal to 0, because all the points in the xy plane have their z coordinate being 0. In fact, that's the distinguishing factor of the xy plane, is that the third coordinates, the z coordinate, is 0. Okay, so we set z equal to 0, so we have 0 equals -3 plus t, and that gives us that t is 3. And now that we know that t is 3, we can plug in 3 for t in each of these equations. Well, there's no place to even plug it in here for x. X is constant, so x is -2. Y is 4 plus 2t, or 4 plus 2 times 3, which gives us 10. And then z, I plugged in 3 for t, but I didn't even really need to plug it in. I knew it was going to be 0. Right? So notice our point is -2, 10, 0. Okay, so this line, that's where it crosses the xy plane. Now, where does it cross the xz plane? You set y equal to 0. You end up getting t equals -2. If you do that, plug it in, you get this point. The more interesting case, though, is the yz plane. So that's when x is 0, is when you're in the yz plane. But notice that x is never 0. Okay, if you set 0 equal to x, there's no value of t that's going to make -2 equal to 0. So what does that mean? Well, that means that the line doesn't actually intersect the yz plane. Now, how is that possible? Well, imagine the yz plane. Imagine as a plane. Could you have a line in 3 space that never passes through that yz plane? Yeah, because the line could just run kind of parallel to that plane, right? Without ever actually going through the plane, without ever actually puncturing through the plane. It just sort of runs along parallel to it. So it's definitely possible. And in fact, that's exactly what would happen in this case.